Hey and welcome back. Uh, this video is for discussing power analysis in circuits and networks. So we have a resistor with a potential Vt across it, and simply power delivered to the resistor is Vt of v square of t by r. And if V is a time varying signal, we can introduce average power, define average power. uh, Average PR is equal to 1 by T time, and the integrate the power V square of T by R over dt, uh, and where capital T is the time period of the periodic signal, and we'll get the average power in one oscillation, in one period of the signal. So this is where we introduce the root mean square voltage. That is, we define Vrms is equal to square root 1 by capital T integration 0 to T V square of T dt. So the application of Vrms can be seen right from the average power which we derived for the resistor. That is, it if Vrms be applied to the resistor, uh, in this case, then RMS square by R will directly give me the average power delivered to the resistor, that is in one time period. So if we have a sinusoidal voltage, that is Vp cos omega t plus phi, the cos square term on integration will give half, and Vrms will turn out to be the peak voltage Vp divided by square root 2. So Vp by root 2 is the RMS voltage for a sinusoidal signal here. And based on that, let's try to analyze a general load. So let's say a general load having impedance Z has Vt potential drop across it and current I of t. Now, in phasors, it can be, V of t can be represented as V bar exponential j omega t and I bar exponential j omega t for current. What is power instantaneously at that instant? Well, power is actual current flowing through the load times actual potential drop across it. So average power will be small I of t, small v of t dt, and integration 0 to t 1 by t to get the average power over the time period. But what is the actual current flowing through it? That is the real part of the phasor, real part of the phasor. So that will be v bar exponential j omega t is real part, and real part is z plus z bar by 2. Applying this property for voltage and current and integrating on 0 to t, we'll get something like this, that can be further simplified to half of real part of v bar I star. Note that v bar I star means that we are taking the phase difference with respect to voltage, the implication of which we'll see later. And this is the average power, the average power delivered to a load, that will be half of real part v bar times I star. Now, uh, although that is the actual power, we define a few more terms. That is, the first term being the complex power. Complex power is v bar I r star by 2, the real part of which gives us the real average power. And this is how we calculate power delivered to different loads. Let's say R, C, and L are different circuits. So you can clearly see that average power delivered to the resistor will be Vp square by 2R. For the capacitor and inductor, it will turn out to be a complex value, meaning that there will be no real power delivered in one time period, and so on. So continuing the same discussion, we have V bar, the phasor, let's say it turns out to be Vp times exponential j phi, and for I bar, the phasor turns out to be Ip, the peak current, times exponential j theta. So the complex power P bar will be Vp Ip by 2 exponential j phi minus theta, and that will be reduced to cos phi minus theta plus j sine phi minus theta. So this is the complex average power. The modulus of this quantity is what we call the apparent power, that is Vp Ip by 2. The unit of this is V dot A. We don't use watt here. What is reserved for the real power, the actual power delivered to the load, that is the real part of this complex power, that is VPIP by 2 cos phi minus theta. And this as the unit, as I said, what, and this is called the real power. Third one being the imaginary part of this complex power, that is VPIP by 2 sin phi minus theta. This is what we call the reactive power, the unit again being VA, or also represented as VAR as well, that is volt ampere, and R stands for reactive. These are some terminologies that we must be very familiar and remember. And the power factor is another term defined, that is real part of the power delivered divided by the modulus of the power, that is basically cos phi minus theta, cosine of the phase difference. And after having discussed this, there is one more small point, that is in practical systems, uh, it is uh, it is required that the effective impedance of any network be real, because when the power is being transmitted from large distances, uh, having a reactance in the effective impedance uh, makes the energy flow back and forth from the source to the load, and this causes more transmission loss on the transmission lines, which the power supplier has to bear. So they do charge some extra amount for this. So to avoid that, we use a capacitor or an inductor connected in parallel to the load that we have, just to correct the net impedance, so as to get a real impedance, the real value, a real impedance, so that it acts as a resistor and just draws power. This also means that I and V will be in phase, and the power factor will be 1 in an ideal case. But in practice, it is tried to get the power factor as close to 1 as possible. Okay, so coming back to the maximum power theorem that we discussed for DC and resistors, in a complex case, what happens is let's say we have V bar as the voltage phasor, the Thevenin impedance, that is RTH plus X THJ, and a load, that is RL plus JXL. So we want to maximize the power delivered to the load from this circuit. This Thevenin equivalent may be a representation of a larger network, and uh, to maximize the power delivered, let's see what the equations say. So just calculate the voltage across the load, and we have power is again half of the real part of the voltage across it times the current conjugate. And on solving and simplifying this expression, this term is what we get. So for maximum, it is clear that ZTH and should be equal to minus uh, XTH should be equal to minus XL, and RL should be equal to RTH. The XL equals minus XTH is what we call the conjugate matching. That means that the net impedance seen by the voltage source is zero. There is no, the reactance. The net reactance is zero. Only resistance is seen by the load, and RTH is equal to RL, the same way we found for the previous case. This maximizes the power, and this maximum power turns out to be uh, half of mod V square by 4 RTH on an average power. So this concludes the power analysis. Uh, some small topics left, that is something about mutual inductors and three-phase systems. Then see you in those videos, and I hope this is helping. I hope this helps. uh, okay, and thank you for watching. See you there.